So, to start with vectors, suppose let us collect all the physical quantities which we have. So if you collect all the physical quantities, you will find that there are physical quantities. If you have a list of physical quantities, you will find that in this list, some of the physical quantities response has a sense of direction. It means if the direction is not given to that physical quantities, that physical quantities is not comprehensible or not understandable. Suppose we say that a force acts on this block kept on the table, and a force acts on this. The first question that comes to your mind, that in which direction the force acts, because unless the direction of the force is provided, the motion cannot be predicted, because if you apply the force from this side, the block will move along this side, or otherwise if you apply the force in the opposite direction, the block will move in this way. So unless the direction of the force is applied, it is meaningless to say that this much force acts. So there are quantities which has a sense of direction. All those quantities which has a sense of direction and follow a certain rule of addition, they are called vectors. So physical quantities can be divided into two broad categories. One that depends only on their magnitudes, as for example mass. If we say mass is 10 kilogram, it does not require any direction. So the mass is 10 kilogram, temperature, it also not requires direction. So all these physical quantities, they have simply magnitudes. They are called scalars. Scalars have magnitudes only. Examples of scalars are mass, length, time, temperature, and so on, etc. But there are physical quantities which has magnitude as well as both magnitudes as well as direction. Those are called vectors. They have magnitudes and direction. And one more, magnitudes and direction, then one more that is it must follow the vector of addition. It must follow the vector law of addition. So we should say law of addition. Okay. Follow the vector law of addition. So vectors must have these three qualities. They must have magnitudes, direction, must follow the vector of addition. There are physical quantities which though have magnitudes and direction, but they are not vectors because they do not follow the vector of addition. As for example, electric current. Electric current has a magnitude and a direction also. Direction from positive to potential to negative potential. Electric current flows from positive potential to negative potential. That is, the direction is given from positive to negative and has some values, 5 ampere or 10 ampere. That what memory they have magnitude and vector, but they do not follow the law of addition. That's why they are not vectors. Similarly, time has a sense of direction from past to present to future, but still they are not vectors because they do not follow the vector law of addition. So now in physics we usually represent physical quantities by symbols, usually Greek symbols or Greek alphabets or Roman alphabet or English alphabet. For example, we write M for mass, T for time, V for speed, and F for force, A for acceleration. In order to differentiate which of these are vectors, in order to differentiate which of them, we know that force is a vector quantity because it has a magnitude as well as direction. So it must be represented by some other symbol, and that is, in order to differentiate from scalar to vector, we add an arrow overhead, give an arrow overhead to represent that this is a vector quantity and this is a scalar quantity. If we write V as like this, it means this is a velocity vector and this is a scalar. If length is represented by say L, and if we write it like this, it means this is a vector. So in order to differentiate between a scalar and a vector, what we do is draw an arrow overhead. Okay. Now vectors have some very special properties, that they can be represented geometrically on the blackboard or a copy. So suppose I have a vector, displacement vector A, which is say 10 meter east. So it is a displacement vector which has a magnitude of, this is its magnitude, and this part is direction. So it has both magnitude and direction. In order to represent it geometrically on your copy, what we'll do that, it means this represents a displacement 10 meter towards east. First of all, we have to find a reference point from where this east measurement is taking place. East, if you cannot draw, if you suppose we have taken this as our reference frame. And this is our north, south, east, west. Now suppose I have taken this as a reference point, starting from this point, 10 meter east. So you are moving from 10 meter east, but you cannot go, 10 meter east cannot be drawn on the copy. So what we have to do is to convert this 10 meter into suitable scale. So let 2 meter is 1 centimeter. It means if you draw 5 centimeter line on this blackboard, that will represent this vector along, and the direction is east. So this is 5 centimeter. Okay. Five centimeter in the blackboard will be very small. I have taken inch, 5 inch. You can take centimeter. So this means the point of the arrow represents its direction. So this arrow represents this vector. Now suppose we have another vector and say it's 20 meter east. It means the length of this vector must be double of this. So this will be, if you suppose start from this point, and 10 means 10-inch line. So this represents the vector B. You have found here that the length of the arrow is proportional to their magnitudes. The more the length, the more the magnitude. And the point of the arrow represents the direction. So now suppose we have another vector C. This is 10 meter west. So the 10 meter west will be along this direction. Means if you draw 10 meter west, obviously this vector and this vector is different. So we can say that vector A is not equal to vector C, although their magnitudes are same. Magnitudes are same. The magnitude of a vector is written within 2 bars. So this gives you magnitude. Although magnitudes are equal, 10 meter, this is also 10 meter, A is also 10 meter, C is also 10 meter, but the direction are different, so the vectors are different. A is not equal to C. A leads you to 10 meter to east, and this leads you to 10 meter towards west. Now suppose there is another vector, D. This again 10 meter east. This means this vector is of the same length as that of A and same direction east, the same direction east. So this is again from this we can infer that these two vectors are same. A so concludingly we can say that the length of the arrow represents its magnitude, the point of the arrow represents direction, and the parallel vectors of same magnitudes are equal. So, the concluding we can write that first of all, to draw vectors geometrically on your copy, first you have to take a reference point. So, to draw vectors geometrically, first of all you have to take a reference point, a reference axis. Number 2, convert the magnitude of the vector in suitable scale. The length of the arrow represents the magnitude of the vector. The magnitude of the vector and and the point of the arrow of the represents its direction. And fourth point is parallel vectors of same magnitudes are equal. Parallel vectors of same magnitudes are equal. So to draw vectors geometrically, first of all we have to choose a reference frame or reference axis, convert the magnitudes into suitable scale, then draw an arrow, and the length of the arrow will represents the length of the arrow will represents the magnitude, and the point will represent the direction. Parallel vectors of same magnitudes are okay. Now, suppose this is our reference point. Suppose you are standing here on the road, and someone asked for the railway station. You know that there is this. Suppose this point is A, and there is a railway station is this point is represented by C. But there is no road. You have to walk to go to the railway station. We have two routes. Suppose we have two routes only. So one route is towards means we have to walk certain distance along say north, and suppose this point is B, which means this is the displacement from A to B, and then I have to turn towards east to reach the station C. It means the sum of the vectors A to B, this displacement vector, plus BC displacement vector gives you the displacement from A to so vector AC can be written as vector AB plus vector BC. Okay. Is it correct? But if you measure the length of this, and the length of this will not be equal to the length of this. Vectorially this is correct. The displacement AC is equal to displacement AB plus BC. But magnitude wise this is not equal. It means AC, mod of AC is not equal to mod of AB plus mod of BC. It means if this is 3 and this is 4, this will not be equal to 7. So it means 3 plus 4 is not going here to become 7. But if you measure the magnitudes only, this must be have 7. So it means this is the scalar algebra is different from vector algebra. In vector algebra this is true. but scalar wise it is not true. So from now on, we have vectors algebra, different algebra. We have vectors addition is different, vectors subtraction will be different, vector multiplication will be different. So the whole algebra vector is different from the scalar algebra. So now suppose we have another root. Another route means you can first walk towards the east direction and then towards north, and you again reach the railway station. Same point. It means again AC is equal to AD plus DC. One root is this, another root is this. Now AD is parallel to BC and of same length, and we have just seen that parallel vectors of same matrix are equal, so AD must be equal to BC. So it is AD is equal to DC. Similarly, DC is equal to AB. Substitute the values here in question 2. This becomes AC is equal to BC plus AB. Suppose this is question 3. Now question 1 and 3, the left hand side of the 1 and 3 are same. It means AB plus BC is equal to BC plus AB. So concludingly we can write that AB plus BC is equal to BC plus AB. It means they commutes. Although vector algebra is different from scalar algebra, but they commute like scalar numbers. In scalar quantity, we know that scalar number, we know that 4 plus 5 must be equal to 5. Although the algebra is different from scalar algebra, but still they commute. So this is one of the basic principles of the addition of vectors. So the vector, this is called the commutative law of addition. Commutative law of addition of vectors. We can write here heading commutative law. Now, again considering the same A to C, but with 3 roots. Starting from A to C, we have to go from A to C, but with 3 different, some of 3 different paths. So, suppose to reach A to C, we have to first we have to go through this one, that this suppose B, and then from say some other point D, and then from D2 So here AC is now the sum of three vectors AB plus BD plus DC. Okay. And this is equal to AC. Now, someone found another route which is easier in order to go from A to B, B to D to C. Someone has found that there is a route here also, some bylanes that leads directly from A to D, and then from D to C you can again reach the station. So there is another route, and this is the bylane route, not so. Someone found that there is another route. Instead of going from A to B, B to D to C, found that directly we can go from this A to D and then the D to C. Which means this person has shortened this length, AB plus BD. So then another route is that AC is AD plus DC. But AD is how much? AD is equal to AB plus BD. So substitute this value here, equation 2. This becomes AC is equal to AB plus BD plus DC. Now suppose there is one more route, and that is instead of going A, B, D, DC, someone found that there is a route from A to B, you can directly reach the point C, and by this route. Alternatively, there is another route, and that is AC can be, this displacement can be written as a sum of AB plus BC. But BC has shortened this BD plus DC. So it will, but BC is BD plus. So if you substitute this value here, it is here B instead of BC. So this will become AC is equal to AB plus BD plus BC. So the left hand side of both 3 and 4 are same. It is if you the sum of AB plus BD added to its DC gives you the same result as AB added with sum of BD plus DC. It means AB plus BD plus DC is equal to AB plus BD plus BC. This is called the associative law of addition of vectors. So headline will be associated law. Okay. Thus geometrically we have found that the vectors can be added like adding, suppose the vectors can be added like this. Suppose vector, this is vector A. Now you have to add the vector B. You have to substitute the tail of the vector B on the head of the vector A. This will give you vector. Now you have to add another vector, say vector C to be added, and that the tail of that C must be kept on the head of the B. It means you have the final displacement is from A. This one is the final displacement. This is called the resultant. It means the sum of A plus B plus C is given by this R. So R is A plus B plus C. It means to add vectors geometrically, arrange the vectors in order such that the tail of the succeeding vector lies on the head of the preceding one. A straight line or an arrow from the tail of the initial to the head of the final vector gives you the resultant. So you add vectors geometrically. Arrange the vectors in order. In order such that the tail of the succeeding vector lies on the head of the preceding vector. The arrow that from the tail of the initial to the head of the final represents arrow an arrow directed from the tail of the initial to the head final vector represents the resultant. So all these plus C. So if this is called resultant, so okay. Here R is called the resultant. And these are called components. Components of the R, vector R, and resultant of the vectors A, B, and C. So R is the resultant of the vectors A, B, and C, and A, B, C are called the components of the vector R. Now, suppose you again arrange the vectors in order, head, tail. Suppose this is the vector A, and this is the vector B, and this is C, and this is the vector D. Are arranging in order, and this is the vector. The resultant of this will be nothing, 0, because it coincides, not from initial to the head, the final coincides. So the resultant of this is A plus B plus C plus D plus E equal to 0. It means if the vectors are arranged in order such that they form a closed path, the resultant is 0. So concludingly we can write that if the vectors are arranged in order and they form a closed path, then the resultant is So all these about the introduction of the vectors, and in the next class we will add theoretically some of the vectors, some problems on addition we will do next in the next class. Okay.